Hi there. Okay, so in this video, I want to show you how to approach problem 7 of assignment 6. This is one that involves a resistor and an inductor, and it's your one chance to get some experience using the exponential formulas involved. So the basic problem is stated like this. You will have different numbers in all these cases. But for me, it says a resistor of resistance 10 ohms is connected in series with an inductor with inductance L is 15 millihenries. The RL, or resistance inductance combination, is connected to a variable voltage supply with voltage equals 12 volts by a switch as shown. So you have a power supply hooked up to a switch, a resistor, and an inductor. So you are asked three different things. I'm going through all three to start with for an important reason. First of all, what is the time constant of this combination of things in seconds? Then the power supply is set to maintain a constant voltage of 12 volts, same as said here, and the switch is closed. Calculate the current in amperes through the circuit at some time 0.055 milliseconds after the switch is closed. Okay. And then part C, calculate the current through the circuit in amperes after the switch has been closed a long time. Now, this is a problem where if you go through step by step, you can potentially get stuck. And so I want to kind of highlight to you how I would approach this. This is one of those problems where being able to see things, what's simple and what's complex, can be a little not straightforward. So in this case, it's worth first considering A and C, and then only then move to B. Okay? So let's just start with part A for simplicity's sake. So part A is, what is the time constant in seconds? So now we do our usual tricks. We have to approach this in the same way we've done in the past. First of all, we write down what we're interested in. Well, we're interested in this time constant tau. And that's what we want. What do we know? Well, we know the voltage that the battery puts out is 12 volts. We know the resistance of the resistor is, make sure I do this right, 10 ohms. And we know the inductance of the inductor is 15 millihenries, or if we want to be more pedantic about it, 0.015 henries. Those are the things we've been given. Now, our next question is, what relates what we know to what we want? Well, as you saw in the previous video, there is a relationship between this time constant and the ratio of L over R. Oh, well, we know L, we know R, and so we can calculate tau. Yay, that's perfectly reasonable. And so all we have to do is sub in the numbers for these two things and figure out what the time constant is. So let's try that out. So we get the L is 0.015. We divide that by the resistance R, which is 10 in this case. It'll be different for your problem, and just submit that. And what do we get? We get that is correct. That amounts to, just to write it down here, that equals 0.0015 seconds. Or, and I recommend you check this yourself, 1.5 milliseconds. So that's the time scale over which the circuit's current can change. And that's just an important thing to understand. Okay, that's getting a number out. Hopefully that's not too surprising. So that's all well and good. But now let's look at the other parts of this problem. And as I said, it turns out that for this, we're going to want to focus on part C before doing part B. And the reason for that is simplicity. We have a formula for how the current can change with time that involves this time constant. But that formula is a little more complicated than we have to deal with, and so it can be a little intimidating to start with. This question is actually easier. Calculate the current through the circuit in amperes after the switch has been closed for a long time. Now, in this case, what are we interested in? Well, we're not interested in tau now. We're interested in the current, which is designated with I. I'm going to call it I naught because it's the current when everything is stable. So here's the thing. When the switch has been closed for a long time, everything is settled out. The current's not changing anymore. Remember, the current changes quickly when the switch is thrown, but then it settles out. When it settles out, the current's not changing and the inductor does nothing. So all we have is is basically a power supply and a resistor. So what we could use in this case is Ohm's law. I is V over R. Because at this time, at the end of this thing, at very long times from after the switch is thrown, the inductor doesn't matter. This is just a resistive circuit. So if that's right, and we could just use Ohm's law, which again is just V equals I naught R, then we can solve that for I and write it down like this and just stick in the numbers. In this case, the current is 12 volts divided by 10 ohms, going to be 1.2 amps. And in fact, that is correct. So we can actually say, getting rid of some extraneous things, that the current at long times is just 1.2 amps. Cool, great, awesome. Now we're actually in a good position to approach part B. Now we're asked something a little more complicated. The power supply is set to maintain a constant voltage at V equals 12 volts. When the switch is closed, calculate the current in amperes through the circuit at a time of 0.055 milliseconds after the switch is closed. So now to do that, we need to calculate what is I. And I will say, for those of you who are curious, why are they talking about I with lowercase i's instead of capital I's. This is just a generic prescription for when currents are AC, when currents are time variable. Different people use different conventions. If you wanted to use capital I's here, that would be totally fine. So we want I at a specific time, and we're told the time t is 0.055 milliseconds. Okay, so again, we have a bunch of stuff we know, and we have this thing we want to figure out. What relates what we know to what we want to figure out? Well, we have an expression for how I varies with time. This is the formula I showed at the end of the last video. It is I naught times 1 minus this E number minus T over the ratio of L over R, which this problem calls tau. And I apologize for my slim crude drawing, but we can deal with it. So we have this relationship. Now we know I1, we've got that. This is what part C told us. This is why we did that first. We know T, it's right there. We know tau, we calculated in part A. So we can do all of this. Everything we need is there. We just have to stick in the numbers to make this work. Now, if you're the kind of person who is using this to do the calculation, you might go, great, I'm going to do that. Let's do it. So I naught, I already know, is 1.2. Okay, multiply by 1 minus E. E is not here. That is irksome. You might see this E and hope it's the same thing. That's not it. That produces a 10 to the something, which is not very useful in this case. You might think, oh, do I have to get a calculator or something? No, you don't. The thing is, remember, E is just a number. It's 2.73. That is what E is. People like to write E because it makes all of our equations look prettier. But it could just be, it's actually 2.73 and a whole bunch of other decimals. Like pi, it's just a number. So all you have to do is replace E with what its value is, 2.73. And then we need to raise that to minus the ratio of this time, 0.055, to this time constant, 1.5. Notice I'm using the same units, milliseconds, milliseconds. Close the parenthesis and close the parenthesis. And so we can submit that and see if we get the right answer. We did, yay. Now notice this, at this time, the current is 0.04 amps. So this is a short time compared to this. So the current hasn't had time to get going very much at this time. It takes several milliseconds for the current to change. And that's what this problem is showing. Now, in your particular case, you'll get different numbers for all of this. So you might get slightly different answers. Hopefully this gives you a chance, though, to see how to approach this problem and how currents can change. Anyway, thank you again for your attention.